Yesterday we talked about the field. So what is field? We said that the field is a capacity. Field has a capacity to do something. For example, I talked about a temperature field. If you have, consider this is your living room have windows. Your living room of course have windows, another windows, your ceiling, floor, and maybe a radiator. So if you take a thermometer and you bring it to different places, the thermometer will read different temperature. Okay, and what can you do with this field? Well, it has capacity to do something. If you bring, I said yesterday, ice to close to the radiator, ice will melt. If you bring coronavirus, for example, the coronavirus will, what will field do to coronavirus? Well, if the field has 150 degree Fahrenheit, or I don't know how much 150 degree to Celsius, maybe 66 degrees Celsius, then the coronavirus will die. If you place coronavirus inside this tense field, the coronavirus will die inside this temperature field. Okay, so that's the tense field can do. Now, this is an analogy to understand the real field. Today we're gonna again talk about the gravitational field and electric field. Okay, so now the planet approximation of Earth, we talked about it yesterday. So if this is the Earth, how can you measure the field and the direction of the force? Before we do that, I'm going to give you another definition of field. Okay, yesterday I gave you field has a capacity to do something. What type of mass experience force? Let's be precise. We're going to call it point mass. Right. So field. So today our definition is a little bit more advanced. This definition is for analogy of temperature field, and this definition is a textbook definition. Field is a space where point mass experience force. What are we talking about? Is there any point mass? We have the Earth, but where is the point mass? Let's put a point mass. This is a point mass. If I put a point mass, I'm going to call it point mass. Field is a space. So field is a space where point mass experience force. So this point mass now experience force. What direction? Okay. So this is the point mass. Now point mass, all of a sudden, if you put the point mass above the Earth, point mass will experience force. What type of force? Attractive force. Okay, so this is the gravitational force. A charge. How do I know what type of charge I have?
Now pause the video and try your own.
Well, this is I'm gonna call it source charge. How do I know what type of sources? I have two options, positive or negative. How do I supposed to know it is positive or negative? Well, the point charge. If I put a point charge over here, then I would know. How? Field is a space where point charge experience force. Okay? Alright, so this definition of where point charge experience force. Now, if point charge experience a force, then what type of charge it is? Positive charge. I told you that if this is the Earth and it's a point mass Okay, the point mass will experience some force. That's the field. That's the definition of field. Point mass will experience some force. Okay, and if you have a charge, source charge, how do you know whether it is a positive or negative? Well, you put a point charge. Point charge. Sometimes they call it test charge. All right. If a field lines goes outward radially, then we know that the source charge is positive. Now we're gonna start the last one with one question. Then what is field lines? We know what is field. The field is a space. Field is a space where a point charge. Field is a space where a point charge experience force. Okay. Now then, what is field lines? Show the reaction of the force on point mass or charge. So, all right. So now let's start with the force of gravity and the universal force of gravity and derived the gravitational field. So we know that F is equal to what is the force? M is small m over r squared. We know that, right? So now if this is u, then you experience some attractive force. Okay, so I'm going to call, if this is u and this is earth and this is earth, you experience some attractive force toward the earth. You accelerate downward. Okay, if this is u, if someone places you a little above the earth, you accelerate downward because you feel some attractive forces. Okay, then this must be what? Then this must be A. Oh, voila. How do you know this must be A? I'm going to prove it. Gm over r squared is equal to A. Is Newton, meter squared, and kilogram squared. Okay, and this is mass. Mass is kilogram, and this is r squared. R squared is meter squared. Okay. Let's see whether they make sense. Yeah, they do make sense. So is equal to A. Okay, so now let's cancel them. Meter square cancel. Kg goes to kg just once. So what do you have over here? Newton over kilogram is equal to A. What is Newton, by the way? Newton is kilogram meter per second squared, and on the downstairs you have kilogram is equal to A. Kilogram cancel. Voila! Acceleration is meter per second squared. Yes. So gm r squared is acceleration. So we replace it by that. All right. So we're gonna write just like Newton wrote it. Am. No, we don't write am. We write ma. If you are above the earth, we call A, but we have a special notation for that. That is a small g, which is 9.8. So then we have mg. So we prove that Newton's third law and Newton's second law are the same. Okay, that's the proof. All right, now we know the gravitational field. Gravitational field is F over m. So F over m is what? G m r squared, which is 9.8 meter per second squared. What a beauty. Now we're going to use the same thing. We're going to prove that over there. Now this time we're going to prove the Coulomb's law. Okay, so let's do it over here. So F is equal to K Q1 Q2 over R squared. Now we know one thing, that this is what? This is E. EQ. Now I'm going to prove, just like the way I prove over here, I'm going to prove that this is E. So K Q1 R squared is equal to E. That's what I said, right? Because E is equal to Newton over meter, SI unit. Alright, now K is what? Newton, meter square over Coulomb square. And then Coulomb is, 1 Coulomb is, 1 charge is Coulomb. And this is meter square, which is N over M. Because N over M is E. Alright, so meter square cancel. We have Newton Coulomb over Q square. Alright? Oh, not Q square, Coulomb square. So C goes to C once. So N over C. This must be C. I'm still in the mass mode. This is C. C for charge. C is the Coulomb, SI unit for charge. So N over C is equal to N over C must be E. Okay? So that's E comes from there. We just proved that E is equal to this. Alright? So then electric field must be what? F over Q. Voila! Electric field is F over Q. Alright, now I'm going to give you an exit slip. So exit slip.
Let's finish today's remote learning with an exit slip.
I'm going to use the same problem I gave you. Alright, so this is our George says. Our George says is positive. Mu microcoulomb. Let's say 25 microcoulomb. Alright? Okay? We already know that this is, we even don't know whether it is positive or negative. So we need to put temperatures. The temperatures. 75 centimeter away. Okay? If we put the temperature 75 centimeter away, now all of a sudden we know that this is, by looking at the fill line, we know that this is a positive charge. Good. I want you to find the magnitude of electric field. Pause the video and do it to your own.
Now pause the video and try your own.
Magnitude of electric field would be what? F equal F over Q, but you cannot use that. So you have to use this formula. K Q 1 over R squared. Because I did not give you this one, this charge, I did not give you the value of this one. So 9.9 times 10 raised to negative 9. And Q is 25. Be careful. 25 times 10 raised to negative 6. And 75 centimeter is 75 divided by 100, which is 0.75 square.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.